Welcome to 50th lecture on computational mathematics with SageMath. In this lecture, we will explore solving ordinary differential equations of order 1 and 2 using SageMath. So first let us look at what are the facilities or inbuilt methods which are available in SageMath in order to solve differential equations. So there are several functions available in SageMath. One is DE-solve to find general solution of first and second order ordinary differential equations, and it uses maxima in the background. It also has DE-solve underscore system. We already made use of this when we looked at application of eigenvalues, eigenvectors to solve system of ordinary linear differential equations. Then you have DE-solve Laplace. It solves initial value problems using Laplace transforms. And then it also has numerical methods like Euler method. You can have Euler methods method 2 cross 2, that is first order system of ordinary differential equations, and then you can also plot graph of the solution of system of ordinary differential equations. And then you also have RK4 method including RK4 method for system of linear system of first order differential equations. And it also, you can also use ODE INT, DE-solve underscore ODE INT. This actually solves numerically a system of first order ordinary differential equations, and it uses SciPy integrate module. So these are some of the default facilities available in SageMath in order to solve differential equations. Right. Now let us start with an example. Suppose we want to solve this differential equation, first order differential equation dy dx is equal to x into 1 minus x square upon y into 2 minus y. So first thing we will look at how to plot slope fields associated to this differential equation. So when we say slope field, what does it mean? So dy by dx is nothing but slope of the curve y equal to f of x, right. So this is your y equal to f of x. So at every point you have the slope which is given by this value. So at each point the slope field will give you a tangent to this curve at that particular point xy. So let us see how we can plot. So Sage has inbuilt function known as plot slope field in order to plot slope field of a given function, right. So here we define f of x y is equal to the right hand side of this ordinary differential equation, and then we use plot underscore slope field, and then let us reduce the figure size is equal to 4, and then you will see, right. So this is the slope field. So for example at this point if I look at this tangent is along this line and so on. So at each point it plots a small line which is you can think of as a line chopped off from the tangent line and in the direction of the slope of the function, right. You can also plot streamline plot. You can use streamline plot. So this will plot the curve, not just the tangent, but it will plot the curve. So let us look at that. Again we are plotting between minus 2 and 2 x value and y value also between minus 2 and 2. So this is the streamline plot. You can think of, for example, if I think of this point. So let us say this point is 0 comma 1. So this is the curve passing through 0 comma 1. So it actually it will be a solution of this differential equation with initial value x0 is equal to 1. So this is how the curve will look like, the solution curve will look like. We also call this solution curve as integral curves. We can try to plot both these things together, the solution curve, that is integral curve, along with the slope field. So that's so you can see here, for example, if I look at this curve, this is how the slope field is moving. So of course it is quite easy to see that no two slope curve, no two integral curve will intersect. Right. Now let us look at and you can also plot this streamline plot through a set of points. So if we wanted to plot only one solution curve, let us say 0 comma minus 1, this for example let us say this curve. So we can simply point mention an option called start points, then you will see the option. You can look at help on streamline plot, it will tell you how to use set of points from which you want to plot the solution curve or this integral curve. Now as I said, Sage has inbuilt function namely DE-solve to solve ordinary differential equation of order 1 and 2. So in this case let us see how it works. So the function is DE-solve, you need to give the differential equation, you need to see give what is the variable and initial condition if it is any, otherwise it will give you general solution and initial variable name, right, and you can also mention what is the method it is using. So it has some certain methods which you can display, right. So you can of course take help on this DE-solve and go through this help document in order to explore more about this function. So let us make use of this. So first we need to declare x as a variable and then y as a function of x, y as a function of x. So function inside this double quote or single quote y and then it is function of x, and then define the differential equation. The differential equation is diff of y with respect to x, derivative of y with respect to x, that is dy dx is equal to the value of the function fxy, that's your that is I could have simply said here fxy, because since we have already defined fxy we can simply say that, and then simply say DE-solve DE differential equation with respect to variable y, other things are default ones, right. So let us run this and see what is the solution it gives. A bit of time, yeah. So this is the solution, it is a solution which is implicitly defined in x and yx, and here this underscore c is actually the constant. Since it is a first degree differential equation, first order differential equation, it will have one constant and you can even ask it to show this solution. So this looks in pretty good form, and this variable, this underscore c, you can obtain by this solution dot variables, and if I say it can have more than one variables. For example, if I look at second order differential equation, it may have two variables, and then you can obtain this. So it says that this variable is underscore c. So and you can replace this by some constant, some other constant, and try to plot graph of this this function, or you can plot set of solution curves. So if you want to, let us say, substitute this instead of capital C, if you want to make it small c, you please say solution dot substitute and then variables 0, substitute it as c. That can be also done. Now you can see that this is replaced by small c. Okay. Now let us see how we can solve this initial value problem. So same problem, dy dx is equal to x into 1 minus x square upon y into 2 minus y, and this initial guess here is y0 is equal to 0. So this is what is known as initial value problem, right. So if you have to solve this, all you need to do is again you call DE-solve and you need to mention the initial condition, right. You can even say ICS is equal to initial condition is equal to 0 comma 1. So this is x0 y0, that is how the initial condition is given, right. So let us ask it to solve. So this is what you get, this is the solution. Now let us try to plot graph of this solution curve and then see how it looks like. So if you want to plot graph of this function, this is the output is in terms of yx. So we will just replace yx by a variable z, and x will be as it is. So, we have to use implicit underscore plot. So, I have just replaced wherever y x by z, and then plot this between x between -2 and 2, z between -2 and 2, right. And let us plot along with the slope field. So, you can see here this is how the solution curve look like, and this is the slope field, right. You can also plot, let us say if I give you another initial condition where let us say here first one was y0, y at 0 is equal to 1, now I am saying y at 0 is equal to 0.5, and then if you try to solve, this is how the solution looks like. And again you can plot graph of the first solution, first initial value problem, that is x is equal x0 is y at x0 is x0, that is 0 is equal to 1, and this is y at 0 is equal to 0.5. So, several curves you can plot together, and you can see that these plots are exactly same as what you got using streamline plot, right. So, let us also add one more solution. Let us say when y at 0 is equal to -1, then how the solution looks like. The solution is this form, and then if you try to plot graph of all these solution curves together, this is how it looks like. So, this is the red color one is the integral curve of this initial value problem where y at 0 is -1, right. So, this is how you can visualize, not only solve the ordinary differential equation, but you can also visualize solution curve using SageMath. So, this helps how the solution looks like, right. Now, let us look at one more example of ordinary first order ordinary differential equation. This is a population growth model, also known as logistic population growth model. So, here P is the population at a time t of certain species or certain, it could be population of human beings, right, and this R is the rate growth rate, and K is what is known as the carrying capacity. So, if the population grows more than this carrying capacity, there is a chance of catastrophe, right. So, we want to solve this differential equation where K is, let us say 2000, that is the carrying capacity, R is 0.01, which is 1%, 1% growth, and initial population is 200. So, how do we do that? So, again let us just define this differential equation. So, this is t is a variable and p is the population function of t, r is 3 by 100, k is 2000, and then solve this solution is equal to d solve d differentiate p with respect to t and r into p into 1 minus p by k, and initial guess is 0 to 100. So, this is how the solution looks like. So, you can see here that throughout there is a constant minus 100 by 10. So, you can replace that, or you can multiply throughout by 3 by minus 3 by 100, and then what you left in this case you can solve for log, there is an inbuilt function to find log solve in terms of log. So, it will find the value of p. So, let us use that. So, first we are multiplying everything by 3 by 100 and then solve this solution, simplified version of this solution, which is in the form of equation for p. So, this is what you get. This is the solution or this is the population at time t. This is a function of exponential function of 3 by 100 t, right. Now, let us look at what is the right hand side of this. This is the right hand side. You can even plot graph of this the population. So, when you plot graph of this population model, this is how it looks like. So, it is a kind of S shape curve, and this is the carrying capacity. So, you can see here that over the period of time this population will be very close to carrying capacity. So, that is a kind of equilibrium in this case you have. You can try to change the carrying capacity, rate of growth rate, etc., and then see how this population changes. So, this kind of thing will help you to kind of visualize this kind of model and look at various parameters and change these various parameters and see how the population changes. So, let me let me say fig size is equal to 4. So yeah, so that is how the solution curves looks like. So it is a period of 0 to 300. If you make it instead of 300 make it 500, then you will see that it will be all very close to this carrying capacity, right. Now what happens in case you have a population which initial population which is more than carrying capacity, then you can see what happens. Initial population instead of 200, suppose I have 5,000, and then what happens, you can try to do that. So suppose if I say 5,000, this is what you get, and let us solve this, and okay, and let us plot the graph of this. So you can see here now it is going down and then down, and then after that, after a certain period, it becomes very close to the carrying capacity, right. So these are the immediate things you can explore using SageMath, right. Okay, so let us look at, if you have to see, we already saw that plotting this streamline plot gives me family of solution curves. So this is one way of plotting, but if you want you can plot that manually. So let me just quickly tell you how to do this. Suppose you have a differential equation log y equal into dy by dx is equal to y into cos 2x, and try to solve this differential equation. The solution is in terms of underscore constant underscore c. So that constant we can see as variables 0, and then we can replace that by small c, and then you see that the solution is now okay. So this is the same thing. Next let us look at this is not required. Let us substitute this capital C by C is equal to 5. You can do that, and then you see what this is how the solution looks like. And now let us you can plot graph of this function. So this is a single solution curve with C value, that constant of integration value is equal to 5. But instead of just one C equal to 5, suppose you want to do it for multiple C value. So let us say you take C value between 1 and 20, substitute the C value between 1 and 20, and let us say not 1 and 20, let us say between 1 and let us say 5 with a step length equal step length, right. So this is what we are doing. We start with initial empty graphics, and in that you just keep on adding this solution curve. So this is how you will see, right. So let us plot graph of this function, right. So that this is the family of solution curves, and you can do the streamline plot. You can look at the streamline plot, and then you will see that the streamline plots will also look like exactly similar to this, right. Okay, next let us look at how to solve second order differential equation, ordinary differential equation. So this is a second order ordinary differential equation, initial value problem. So this is actually homogeneous second order ordinary differential equation with these are initial conditions. We want to solve this. So again what we do, we define this differential equation by taking y as a function of x, and this is the differential equation 5 into second derivative of y with respect to x plus 4 into second derivative of y with respect to x plus 17y is equal to 0, and the initial condition is 0 minus 1 2. So here this is x0, this is y0, and this is y dash at 0. This is the default value, and then this is what the solution looks like. The y, this here it gives you y at x is equal to this. So this is the solution curve. Of course you can find derivative of this second derivative, first derivative, and try to see whether it satisfies the differential equation. That should be an easy task. I will leave that as an exercise, right. Now you can plot graph of this the solution function, that is the integral curve. This is how it looks like. So you can see here as x increases, this will become very close to x axis, right. So this is a kind of some wave, and as you see when the time increases, the wave will die down, right. So you can also solve the same problem without initial condition. So if you do not mention the initial condition, this will give you solution in terms of two constants here, k1 and k2. K1 and k2 are two constants, right. You can see here what are the variables involved. So, it says that k1 and k2 and x is the variable. So, these are the two constants. Again you can replace these two constants by some fixed value and try to plot graph of this function, right. You can also solve boundary value problem. So, suppose in the same differential equation, suppose now the boundary condition is something like this: y at 0 is 1 and y at 2 is equal to 0. And then let us solve this differential equation. So, instead of initial condition, now you have to give a 4 list of 4 elements. This is x0, y0, this is x at 2 and y at 2. So, this is x0, y0, that is and this one is x at 2 and this is value of y at 2, right. So, if you solve this, this is how it looks like. If you try to plot its solution curve just to make sure that it satisfies the initial condition. So, you can see here at x equal to 0 y value is 1 and x equal to 2 y value is 0. So, this is the solution curve, right. You can also check whether the solution at x equal to 0 is 1 and solution at x equal to 2 is 0. So, that is what we get, right. Let me look at one more problem, which is non-homogeneous ordinary differential equation. So, this is a second order differential equation. This is non-homogeneous because right hand side is non-zero, and this is initial value problem because y at 0 is 0 and y dash at 0 is also 0. So, this is actually see almost, I mean, every differential equation will have some physical meaning, and this differential equation also represents it has physical meaning. So, a mass of one sludge stretches a spring of 2 feet and comes to rest at equilibrium, right. The system is attached to a dashpot and that imparts a damping force equal to 8 times the instantaneous velocity of the mass. That is where you see this 8 times y dash. The equation of the motion in this in the external if the external force equal to 8 times 4 sin t is applied. So, that is the force on the right hand side is applied to the system starting at t equal to 0, then this particular problem is governed by this particular differential equation. And if you try to solve this so again the solution is exactly similar. You use DE solve, but the right hand side here is mentioned as equal to 8 into sin 4t, and then you can also give the option called solution underscore method is equal to true. So, it says that it uses a method called variation of parameters, and you can look at what are the other inbuilt methods. So, depending upon the differential equation, nature of the differential equation, the Sage will find appropriate method and it will solve using that method. Of course, you could create your own user defined function in order to solve such differential equations. That should not be very difficult task, and this is the general solution of this ordinary differential equation. Of course, you can find a particular solution of this and all these things, the method which you have done using variation of parameters, all these things can be executed. Now, let us solve this initial value problem. So, in this case the initial value is 0 0 0, that is x at 0 is that is y at 0 is 0 and y dash at 0 is also 0. So, in this case this is how the solution looks like, and you can try to plot graph of this function. So, you can see here that is again a kind of wave, and instead of 4 let us make it 10. This is how it looks like. This is a wave function, right. So, that is how you can solve ordinary differential equation of order 1 and 2 using inbuilt Sage function DE solve, and you can not only plot not only solve this analytically, but you can also plot the solution curves. So, that is the advantage of using this kind of software. You can use it for visualizing the nature of the solution, right. Okay, let me leave few simple exercises. So, these are the 3 exercises. one is again a population growth model, and it is actually about Bengal tigers in the conservation park having carrying capacity 100 and minimum of 10 to survive. So, this is the minimum survival minimum value of the surviving population, right. So, this is governed by this population growth model, and this so here T is the minimal threshold, this is the minimal threshold value of the population to survive. If the population grow at 1% per year with initial population of 15 tigers, then you can draw the slope field with the following values: k is equal to 100, and r should be actually 0.01, not 1, r is equal to 0.01, t is equal to 10, and also solve this for a population at time t. And then next problem is solve this initial value problem, which is the simple one, and with also plot the slope field along with the solution curves, right. And then solve the second order differential equation, this which is initial value problem, and you can also include boundary value problem in this case. Okay, so these are the straightforward problems I have left as practice exercise. So, thank you very much. I'll see you in the next lecture, in which we will look at how to solve ordinary differential equation numerically. So, we will try to explore some of the methods like Euler method and other things. So, basically we will look at Euler methods. We will create our own function as well as we will use inbuilt function. Thank you very much.